swing it. Something like that.
Okay, I'm glad to say that this is a simple pendulum. What I have in my hand, this is a rope or a string. On the rope, we have a mass tied to the string. This arrangement, okay, constitute a simple pendulum. You see, when you were describing, you are always looking at the string, the mass, and then the rector stand. The rector stand is just to give it a support so that this thing oscillates around the support. Here, my hand is a support. So my hand functions as the rector stand. So when we talk about a simple pendulum, we are talking about any mass, not necessarily this metallic mass, or any mass tied to a massless or weightless string. I'm talking about massless or weightless because we don't expect the weight. We always want to neglect the mass or the weight of the string. So when you tie any mass, it can be any mass. It can be inshira, it can be a book, it can be something, any mass to a string, to a massless string, and then made to oscillate. When given a support, you have a simple pendulum. Is that okay? So when I draw this is the support. This is the mass. This is the string. This is the support. I have a simple pendulum. Are we okay?
Yes, please.
All right. So, conical pendulum. In a conical pendulum, we have a simple pendulum like this, but the motion of this is made to oscillate in a different way. This is the support where my hand is. Now, in causing the string, the pendulum to oscillate, okay, this is giving a small angular displacement, theta. Initially, it's like this, okay? Then this is an imaginary vertical. The marker represents an imaginary vertical. Then when the body is given a small angular displacement like this, and then make it oscillate like this. So it's being given a small angular displacement. My hand is the imaginary vertical. So the angle between the marker and then the string is that angular displacement. And it is made to oscillate like this. In a horizontal, the mass describes a circular base. I'll send you a video of this. Okay. The mass M describes a circular base, whilst the string cuts, the motion of the string cuts the shape of a cone. Okay. I'll send you a video so you can picture well. Here, you are not getting the picture. Okay, let me reduce the length. So the motion is like this. The mass describes a circular base, whereas the motion of the string cuts the shape of a cone. Conical pendulum. I'm coming. Let me pick. Okay, the call has even been cut. So this is what we mean by conical pendulum. Please, can you see?
Yes, please.
So
Yes.
the mass describes the circular base, whereas the string cuts the shape of a cone. Hence the name conical pendulum. Let me draw something. So this is the support. This is an imaginary vertical which I use the marker to represent. Then this is the string that is giving a small angular displacement theta. So when the string is oscillating, it gives a shape like this. So we have so the base describes the shape of a circle, whereas the string describes the sweeps or cuts the shape of a cone. Hence the name conical pendulum. Now this is the radius of the circle. This is the length of the string. This is the small angular displacement theta. Okay, this is the mass. The mass exerts some weight. So this is the weight of the string given by mg. Right? Now, in terms of tension, once this is a string, there is a certain level of tension within the string which supports the weight of the mass. So the tension within the string is always directed towards the point of support where we have the support. Once the support is here, the tension is always directed towards the support. Okay. Now, once we have, if we extend this, this weight vector, we realize that this angle alternates with this angle. So once the weight is tilted at an angle theta, of course, in physics, whenever a vector quantity is tilted at an angle theta, we can resolve it into a component, a vertical component, and then a horizontal component. So when we resolve the tension, we have the vertical component, okay, to the tension and then the angle. This side becomes the horizontal, whereas this side becomes the vertical. Please, do you agree with me? The opposite and then the adjacent always refers to the angle. So with the angle, this side will be the horizontal, and then this side becomes the opposite of the angle. Okay, so when we resolve this, we have this component giving us t cos theta. And then we have this component, which is also giving us t sine theta. The vertical component is here. But because of equal vectors, we can resolve t with this side and this side, or use this one. This side, which is t cos theta, is the same as this. This side, which is t sine theta, would still be the same as this part. So in all cases, the direction is this. Please, are you okay with the resolution?
Yes, please.
To all. Let me ask Gloria, Irene, Lauren, Ishra, Patience, and who else? Regina, are you okay with the explanation? Okay. Okay, so we have T sine theta, T cos theta. Now, when we look at vertical equilibrium, we realize that T cos theta component of the tension is balanced by mg, the weight. Then horizontal equilibrium, we realize that the T sine theta component is unbalanced. It has no, this is unbalanced. Let me put the unbalanced. There is no balancer at the other end. It's unbalanced. And this is whenever there is an unbalanced force, a net force, or a resultant force, it brings about acceleration. Okay, because this has no balancer at the other end, that is why in a conical pendulum, it is always, the body is always accelerating towards the center. So whenever you have this arrangement and you turn it, displace it at an angle and you wheel, it is embarking in a circular motion because the unbalanced force, which is the T sine theta component, behaves like a net force which causes the body to accelerate. So the circular motion of the mass, okay, is caused by the unbalanced force T sine theta. And so we equate the unbalanced force T sine theta to the centripetal force which keeps the body in that circular motion. Because the body is in circular motion, okay, and the force which keeps the body in circular motion is also always directed towards the center, and the T sine theta is also directed towards the center of the circle. Then we equate that the T sine theta is equal to the centripetal force which keeps the body in that circular motion. And we do that because we see this component T sine theta directed towards the center of the circle. Once it is, and it's also along the radius. Centripetal force is directed towards the center. It's also directed along the radius. And so this T sine theta component becomes equal to the centripetal force which keeps the body in circular motion. Please, are you okay with the explanation?
Yes, please.
Oh, Mommy John, it's been a while since she joined us. I'm coming in. Let me respond to her. She seems to have challenges joining us. Oh, I'm coming. Okay, so this is it. This gives us equation 2. So the important question is that why do we equate the T sine theta component of the tension to mv squared? One, it is because this is directed towards the center along the radius. And because centripetal force is also directed towards the center along the radius, then the T sine theta component must be the centripetal force, which keeps the body in that circular path. That is the reason. Now, if you divide equation 2 by equation 1, divide equation 2 by equation 1. So left hand side divide by left hand side, right hand side also divide by right hand side. we have T sine theta over T cos theta equal to mv squared on R divided by mg. And this is equal to tan theta. And tan theta is equal to v squared over rg when you simplify. Because the ratio of sine theta to cos theta is equal to tan theta. When you divide mv squared over r by mg, you have this. When you make v the subject, you have v squared is equal to rg times tan of theta. Therefore, v is equal to square root of rg tan theta. This relation or formula also gives us a similar relation we had yesterday about the maximum or the safest speed. Are you done writing? I want to redirect the camera. Are we? Once you are not talking, it means you are. If you recall, yesterday when we looked at a car moving in circular motion on a flat horizontal road, we saw that the maximum velocity v is given as square root of rg square root of mu rg, and this gave us the expression of the maximum velocity or the safest velocity. And we realize that v is directly proportional to the square root of the coefficient of friction, and v is also directly proportional to the square root of the radius. We have a similar situation here too. You see, we've had v to be equal to square root of rg times tan theta. This is the expression of the maximum velocity. So in a conical pendulum, if you have to calculate for the maximum velocity, this is it. And the maximum velocity also relates to, is directly proportional to the square root of the radius, and also directly proportional to the square root of the tangent of the angle of inclination theta. Meaning,
I don't understand what's
it shall come again.
This is how we doing.
Intra, where were you? So after deriving equation 1 and equation 2, we divided equation 2 by 1. Are you okay with the division?
Yes, please.
Good. Then we got tan theta to be equal to v squared over rg. Then we made v the subject. Making v the subject gave us this equation, that v is equal to the square root of rg times the tangent of the angle theta. Are you okay with this?
Yes, please.
Now, this equation is what we are calling as the maximum speed, okay, that can be obtained by a conical pendulum. So if you have to calculate for the maximum speed of the conical pendulum, this is it. It's equal to square root of RG times the tangent of the angle of displacement. Now, this maximum speed depends on some factors or variables. From our formula, we realize that V is directly proportional to the radius of the conical pendulum. And this is the radius. From the where the mass is to the center is R, the radius. So when the radius changes, it will also change the speed. Inshallah, you okay?
Yes, please.
Another factor is the angle. It's also, the maximum speed also depends on the angle, theta. So when the angle changes, it also changes the maximum speed. As for gravity, it is constant on the surface of the earth. So long as its H value is the same on the surface of the earth, we won't use that as a factor which affects V. That is what I'm saying. Are you okay?
Yes, please.
Good. Please, I hope that's okay by all of us. There is another modification of the same relation we can modify. Now, a conical pendulum is a motion and a uniform speed. V at every point must be constant because the level of the body as it rotates is constant. Mamijan, you just joined us, so you follow as we go on. I'll chip in those areas you missed. This is a uniform speed motion because the level of the body when it is revolving constant, and so gravity acting on the body at every point whilst it revolves is constant. So it's a motion of uniform velocity motion. Now this one is also said to be a uniform angular velocity because we suppose the angular displacement with time to be constant. Okay, so because of this, you can be asked to calculate the angular velocity omega of the oscillating body or the revolving body. And you can also be asked to calculate the number of revolutions made within a given time. Okay, the number of revolutions made within a given time. So there's another way to express the formula for the velocity to take care of when we have a situation like this. And this is how to go about that. T, the tension cos theta, which is the vertical component, is equated to mg. Now, the horizontal component T sine theta, instead of equating to mv squared over r, we will equate it to the other formula of centripetal force, m omega squared r, which we obtained. When you divide equation 2 by equation 1, you have T sine theta over T cos theta equal to m omega squared r over mg. So over here, we are bringing in the angular velocity, the constant angular velocity omega, so that we have tan theta equal to omega squared r on g. Let's make omega the subject. When you make omega the subject, you have omega squared is equal to j tan of theta over r. Therefore, omega is equal to the square root of j times tan of theta. So if you are asked to calculate for the angular velocity omega of the revolving mass, this is it. Please, are we okay? Are we okay?
Yes,
Oh,
please.
human beings or beings? Then you can also be asked to calculate for the period, the time taken to make one complete revolution, capital T. And since period is equal to 2 pi on T, sorry, angular velocity is equal to 2 pi on T. When you make T the subject here, if let's substitute it into it, 2 pi on T is equal to J tan theta over R. It shall make T the subject for me. T would be equal to, all of you, please work it out. Work it and then let's make T the subject of the relation. Amidan, are you here?
Yes, please.
Finally. We are making T the subject. Is that true?
I
Tell me.
I got um 4 pi T is equal to 4 pi squared times R on G tan theta.
Okay, so look at it. Look at how I am also going to do the same thing. Irene, are you there? Irene.
Yes,
Irene,
she had
wait.
to go off.
Look at her. For what?
I mean, I'm not sure
Sure of what? You are not sure of what?
why she left.
Okay. So because I'm making T the subject, I'm putting everything under, okay, different roots. So the numerator and then denominator. Now take the reciprocate this term, the left. Okay, Mami Jan, okay, let's go through it. Reciprocate the left hand term and do same to the right hand term. If you do that, you have T on 2 pi is equal to root of R on root of J times tan of theta, isn't it? Class,
Yes,
isn't it?
please.
So that if you make T the subject, you straight away have T is equal to, when you cross my 2 pi times R on J tan theta. Is that what you got?
Yes, please.
Who had a different thing?
Mm.
Who? Mami Jan, what did you get? What did you get? Let's see.
T is equal to
T is equal
square root
to
of
uh
4 pi r on G times
4 pi r within the roots under the root sign.
yes,
4 pi r on what?
G times theta.
No, no. So even if it's like this and you cross multiply, okay, let me use perhaps the steps you used. The steps you used.
Mr. Evia, please, oh, madam, should we square it or should leave the square root sign?
No, you are making T the subject. So assuming this is what I have, 2 pi on T is equal to square root of, I'm breaking them under different root signs. Okay, and I'm making T the subject. Of course, you cross multiply. So you have 2 pi times root of R is equal to T times root of J tan theta, isn't it? Isn't it? Go. So
Yes, please.
if I'm making T the subject, I divide through by root of J tan theta over root of J tan theta. So that this and this will cancel. T therefore is equal to 2 pi times root of R divided by J tan theta, J times tan theta. The same as what I had. So if I'm going your step, this is how I have to get. Okay. So please, it's not like T is under the root sign where you need to square to eliminate the root sign. No. T isn't part of the root sign. So open your eyes when you are doing this.
Yeah,
Hello.
that's what I did. I squared this time.
I suspected that perhaps that's where the problem comes from. Okay. T isn't part of the root sign. It's outside. You are only making T the subject.
Yes, please.
Please, class, are we okay? Lauren, Patience, and the rest of you, are you okay? Now, another modification. So this is how to obtain omega. When you have omega, you can easily determine. You don't even need to use the formula. Once you have a value for omega, omega is equal to 2 pi on capital T. Substitute whatever you have for this, make and then you don't even need to use the formula. Okay. Now, the other modification is that we resolved this in terms of tension, but we can also have this. Are you looking at it? Hey, how many of you are gone? We were 8, including myself, but we've dropped to 6. Patience is here, Inshira is here, Mamijan, Lauren, Gloria. This what's the name? Irene is gone. Who else? Regina. Hey, Asemo, yo. The other modification is this. Earlier, we resolved this in terms of the tension in the string. So, but this is the string. L is the length of the string. The same, this is the radius of the circle. So we can also resolve this in terms of when we find sine of the angle of tail, theta, sine is equal to R on L. Okay, so sine theta can also, in terms of displacement or length, we can say sine theta is also equal to the radius of the circle divided by the length of the string. so that R is equal to L sine theta. But earlier we resolved the tension. We resolved the tension into its vertical and horizontal component. Okay. Now we can also make this the subject, substitute it into this to find an expression for omega. Omega is equal to, let me take omega squared. Omega squared is equal to J tan theta over R. R is this. So this is J tan theta over L sine theta. Now, omega squared is equal to J times sine theta over cos theta, all divided by L sine theta. Okay, so that when we simplify whatever we have here, we have J sine theta over cos theta, all divided by L sine theta over 1. And this is J sine theta cos theta times 1 over L sine theta. So that sine theta would cancel sine theta. And the final results will be J.
Mr. Joa, please can you move the camera to the side of the tube?
Of the,
Can you move it to the right?
I'm coming in. Okay, let me move it up and then continue from there. So let me clear this. So when we substitute R is equal to L sine theta, we finally have omega squared equal to omega squared equal to J over L cos theta. So that when we take the square root of this, we have the square root of J over L cos theta. This is another relation for angular velocity when we substitute radius being equal to length times sine theta. Then 2 pi over t, when we equate to this, we have J on L cos theta. Please help me make t the subject from this. Put pen on paper, make t as the subject, and then report to me.
Mr. Joa,
Hello. Are you true?
yes, please.
What did you get? T is equal to
2 pi square root of L cos theta on G.
2 pi times the square root of
L cos theta
L cos theta
on G.
on G. Patience. Is that what you had? Vision, is
Please,
that
I'm
what
on you.
you're on it? Lauren, is that what you got?
Yes, please.
Ishra?
Yes,
So,
please.
so this is the whole stuff about conical pendulum. It also means that the velocity equation we can also modify. We got V is equal to the square root of RG times tan theta. We can also modify. Once we have an expression for R, and then we can break tan theta down. R is L sine theta. So L sine theta times G times tan theta or sine theta. We can modify this once we have expressions of this sort. Example, let's solve a question using this formulas we've learned. Are you ready? I'm reading. Are you ready?
Yes, please.
An object of mass 10 kilogram, an object of mass 10 kilogram is whirled round a horizontal circle. Is whirled round a horizontal circle of radius 4 meter by a revolving string. Hello.
Can you read the question from the beginning?
Okay, pay attention and listen.
Yes,
An object of mass 10 kilogram is whirled round a horizontal circle of radius 4 meter by a revolving string inclined to the vertical. By a revolving string inclined to the vertical. Hello.
It's one a horizontal string.
A horizontal circle of radius 4 meter by a revolving string inclined to the vertical. Can we continue? If the uniform speed of the object is 5 meters per second, if the uniform speed of the object is 5 meters per second, calculate I, the angle of inclination of the string to the vertical. Calculate I, the angle of inclination of the string to the vertical. I, the tension in the string. The tension in the string. Take gravity, acceleration due to gravity to be 10 meters per second squared. Take acceleration due to gravity to be 10 meters per second squared. Okay, so 3 minutes to try. Give it a try within 3 minutes. Then I also come in, okay? Finished. They won't mind me.
No, I know that.
I'm sure we are true. Eh? The name is here.
Mr. Yeah.
Answer. Are we true?
Something like that.
Lauren, answer. Patience, answer. Mami Jan, answer. Are we true?
No, please.
Okay.
No.
So let's look at it together. There's no time. We are going out for Christmas, so what?
It was black, black. That's a way that black goes.
And shall I mute yourself? Two things you must understand. You see, we have when a string is a mass is tied to a string and weld, horizontal oscillation like this. So here the string is flat. There's no angle. So this is when a mass is tied to a string and weld horizontally. This is it, horizontal rotation, where the string is flat, angle 0. Then in conical pendulum, the rotation is like this. Take note. So here there's an angle the string makes with the vertical. Okay, so there is some difference. The difference is that we have flat rotation, where the string is just flat on the ground and then rotates like this. the angle is 0. We are perceiving that the angle is 0. And then conical pendulum, where the rotation is like this, the string makes an angle. So when a question is given, you must identify which is which. Is it a flat horizontal rotation or a conical pendulum? And so in the question, what will inform you? What will inform whether it's a flat rotation or a conical pendulum? Let's listen to the question. An object of mass 10 kilograms is well drawn horizontally. So this is also a horizontal circle of radius 4 meters by a revolving string inclined to the vertical. So here is being stated that the string is inclined to the vertical. Okay. And we are also being asked to find the angle of inclination. So it means this question is about conical pendulum. It isn't just a horizontal circle or revolution. Please, are we okay? So
Yes,
that's
please.
how to make the difference. We are told the mass is 10 kilograms. So the mass of the object of the pendulum is 10 kilograms. And it's well round, a horizontal circle of radius 4. So the radius of the circle is also 4 meters. By a revolving string inclined to the vertical. If the uniform speed of the object is 5 meters per second, I earlier told you that for conical pendulum, it is a uniform speed motion because gravity on the object at all points is the same. So its speed is 5 meters per second. Calculate the angle of inclination theta and then the tension. So we are looking for theta and T. How do we get the angle of inclination? Using V is equal to square root of RG tan theta, we can easily find it. Because V is given, so instead of V square root, let's use V squared. So 5 squared is equal to the radius, which is 4, gravity is 10, times tan of theta. So tan theta is therefore equal to 25 divided by 40, which is 5/8. So theta is the tan inverse of 5/8. And what did we get? What did we get for theta? Gloria and Co. What did we get for theta?
32.
Pardon?
32.
So 32 degrees. So this is 32 degrees for the angle of inclination. How many of you got this? Yes. Lauren, Patience, Regina, Mamijan, and so on and so on. None of you got it.
Please, I got it.
Okay. Then please, if you didn't get it, please there's a solution. Then the next question is on the tension. Tension. Yes. You can use two different ways. T cos theta is equal to mg, or T sine theta is equal to mv squared over r. Any of this must give you the tension. So T is equal to 10 times 10 divided by cos of 32. Calculate it for me. So 100 divided by cos 32 degrees. Isra, calculate it for me.
Jesus. Hey, my area is loud.
Eh?
This is 117.91.
So approximately 118 Newton. Let's confirm the same thing using the other relation. T sine theta is equal to mv squared over r. Yes. Let's confirm. What have you had? Lauren, today you are quiet. You are so quiet. Laura, you are quiet. Patience, I'm not happy with it. Be talking. Gloria. Gloria. Lauren.
Mr. Yes, sorry, please. I wasn't.
Where did you
I
go?
was called to do something.
You are in
I
a
was called to
classroom.
do something.
No, you are in a classroom. You can't be called.
Oh,
So T sine 32 is equal to mass times the square of the constant speed divided by the radius, which is 4. So 10 by 25 on 4. 5, 2. So 1, 2, 5 divided by 2. So finish it for me. When you finish, you divide that by sine 32. What did you get?
118.
Okay, so the same answer. So each of this method can help you get the same thing. Another question for you to try. I will not come in. This time I'll give you 5 minutes to finish. Are you ready?
Yes, please.
A pendulum bulb of mass 2.0 kilogram is attached to one end of a string. Is attached to one end of a string of length 1.2 meter. Of a string of length 1.2 meter. The bulb moves in a horizontal circle in such a way that in such a way that the strength is inclined at 30 degrees to the vertical. The strength is inclined at 30 degrees, 30 degrees to the vertical. Calculate the tension in the string. Calculate the tension in the string. Gravity
Mr. please
is
take it.
a pendulum bob of mass 2.0 kilogram is attached to one end of a string. One end of a string of length 1.2 meter. The bob moves in a horizontal circle in such a way that the string is inclined at 30 degrees to the vertical. The bob moves in a horizontal circle in such a way that the string is inclined at 30 degrees to the vertical. Calculate the tension in the string. Take J to be equal to 10 meters per second squared. Calculate the tension in the string and take J to be equal to 10 meters per second squared.
Mr. What are we finding?
The tension in the string.
Okay.
Finished.
No, please.
There is this question I'm searching for you. The brain working question. I'm sure you are true.
So please, do you need to use gravity in the solution?
Yeah, gravity is giving us 10 meters per second.
Okay.
I've also sent, I'm going to send you an assignment on the page. Sent. All right, so let's look at this particular question. Then start banking of rules. So if you got 23, 23.09 Newton, you are correct. How many of you got that? 23.09 Newton. Okay, so I have Inshira, Lauren, Patience. Okay. So 3 of you had it. Okay, let's quickly look at it. So a pendulum bob of mass 2.0 kilogram is attached to one end of a string of length. So the mass is 2.0 kilogram. And it's attached to one end. The length of the string is 1.2. Then the bob moves in a horizontal circle in such a way that the string is inclined at an angle of 30 degrees. So theta is 30 degrees to the vertical. If J is given as 10 meters per second, we calculate the tension. So for the tension, T cos theta is equal to mg. Once I know theta, I have mass. I can easily find the tension. So T is mass, which is 2 times 10 divided by cos of 30 degrees. This is 20 divided by 2 root 3 on 2. So this is times 2 on root of 3, which is equal to 40 root 3 on 3. What is 40 divided by 3 times root 3? So 40 root of 3 which is this, divide by 3. 23.09. Or maybe I want to use the other way out. T sine theta is equal to mv squared on r. Okay. V is equal to the square root of rg tan theta. I'm not directly given r, but I know sine theta is equal to r on L. Therefore, r is equal to L sine theta. If r is equal to, let me come here. If r is equal to L sine theta, then 1.2 times sine of 30. Sine 30 is half. So this is equal to 0.6 meter. Therefore, V is equal to root of 0.6 times 10 times tan of 30. Tan 30 is equal to 1 on root 2, which is 1 on root 2 is root 2 on 2. So 5 times 0.6 times root 2. 5 times 0.6 times root of 2, which is this. When you take the square root of this, you have 2.06 as the velocity. 2.06 meter per second. Therefore,
Yeah.
hello,
This San 30 is root 3 on 3 or
no, this is 10, please. Tan 30. That is
root 3 on 3.
it's root 3 on 3.
Yeah.
Eh. This is 30.
That
This is
was
1. This is, oh, this is root 3 on 3. Sorry. It's 1 on root 3. Okay. So let me point it again direct. 0.6 by 10 times 1030 is it. So that when you take the square root of the answer, you have 1.86. Isha, thank you. 1.86. So T is equal to, okay, T sine 30 is equal to mass 2 by 1.86 squared divided by radius, which is, what did we get for radius? I think 0.6. 0.6. So this squared times 2 is this divided by 0.6. There's it. So that when you divide this by 0.5, you have 23.09. So both ways will take you there. Please, are we okay? So you can use any of these methods to find the tension. So simple. Banking of roads. That is if
So
you
please,
don't
I have
have.
a question.
Okay, Lauren.
Okay, so please, if given a question without acceleration due to gravity, do you have to assume it so you can solve?
Usually, if you are not given, you use 10.
Okay.
Okay. If it is not given to you, use 10 meter per second squared. If you are to use 9.8, it will be stated. Okay.
Okay, sir.
Banking of roads. We yesterday learned that when a body is in circular motion, the centripetal force which enables the car to stay within the circular path is provided by the hey, Mami Jan, if a car is in circular motion moving around a bend, the centripetal force which keeps the car in that circular path is provided by the hey, Charlie,
I have no idea.
provided by Gloria. If a car is negotiating a bend, the centripetal force which keeps the car in circular motion is provided by the hey, by who? Okay, let me go
Wait,
to
Mr.
my
Dua, please say it again.
a car in a car negotiating a bend. That centripetal force which keeps the car in circular motion is provided by the
The frictional force
the frictional force between
between
the road surface of the
the
road
car
and
and the car and the road.
the tire.
If
Travina, did you just come?
something like that.
Yeah, look at her, something like that. The late Trifina. I won't buy it the next time. Okay.
Yes, please.
In fact, Trifina, kneel down. Kneel down. That's your punishment. Are you kneeling? Trifina, are you kneeling?
Mm, hmm.
I said kneel down. That's your punishment.
Yes, please.
So the centripetal force is provided by the frictional force between the surface of the road and then the tire. This is what keeps the body, enables the car to stay within the bend. But there is some other situations. Trafina, get up. There is some other
Thank you.
situations or engineering intervention where the car can take a bend without depending on friction, even though it is in circular motion. That is the essence of banking of roads. So in the first one, we see the car to be moving flat within the circular path. So if there is a circle, there's the center of it. Yes. The car is able to move. And this time, because this is flat horizontal circle, when we use the adjective flat, then we mean to say that there is no angle to the radius. In banking of roads, here the road is built in such a way that if this is the road, there's a circular path. The radius makes a certain angle theta with the horizontal. This is the radius of and the car stays like this. So the car moves on a circular path. There's a center, but the road architecture is designed in such a way that the radius of the road makes a certain angle theta with the horizontal, or the outer end of the road is raised. So this is what we call as banking of roads. This is a car, a very beautiful one. But the car glides on the surface of the road, and that surface of the road is inclined at an angle theta with a horizontal. That's the essence. So this is actually the road, that circular part of the road. Okay. Now, why banking of roads? I earlier said that when a road is banked, drivers or motorists are able to go through that circular path or make that turn without depending on the traditional friction, because we earlier saw that when a car is in circular motion, frictional force enables it to stay within the circular path. But over here, cars can be in a circular motion without depending on friction. This is practical. It's on our roads, especially when you are driving on mountainous areas. The road is built in such a way that it is tilted at an angle to the horizontal. So when you are driving on roads, be opening your eyes to banked roads. I don't know if any of you have experienced that before or have seen that, where the road is tilted. So when cars are plowing on such a road, you feel bent. The occupant actually feel bent as if the car is tilted. Who among you have experienced or have seen this engineering design before? Lauren, okay. So, who else? Mention your name. I saw Lauren. Who else? Inshira, okay. Mami Jan, you have not seen it. Okay. Now, what is the essence of banking of roads? Its purpose is to prevent accidents. Prevent accidents because when the road is banked, drivers or motorists can embark on certain speeds, certain maximum speeds without depending on friction. When you depend on friction, if you go beyond a certain threshold of speed, you can easily skid off from the road and then cause accident. So when the road is banked, it prevents accidents. It also prevents wear and tear. Prevents wear and tear of tires and parts of the vehicle and some parts. Why? It is because, you see, once you are dependent on friction, it means friction will certainly oppose motion, and to stay within the circular part, friction must be increased to a certain magnitude. But here is the case, motorists are not dependent on friction. So if I'm not dependent on friction to take a bend, then wear and tear would also be reduced. And then the third aspect is that it enables vehicles or motorists to have a certain maximum allowable speed. Maximum allowed speed or velocity, which you cannot have, which cannot be, which can't be allowed when road is not banked. There are some speed motorists cannot embark on when the road is not banked. No. There's a limit you can go in all cases. But when the road is banked, that limit is higher than when it is not banked. So you can easily go through a certain speed which will be allowed on banked road. But that speed, maximum speed, will certainly not be allowed when the road is not banked. So these are, banking of road is actually an engineering architecture, okay? And it is all usually found at where roads are curvy. So whenever you are traveling, driving, or in your traveling on road, be opening your eyes to areas of banked roads. So we define banking of road as the process of building a road and tilting it at an angle towards the radius. Okay, tilting it at an angle towards the center. Let me write the definition. The process of building a road and tilting it at an angle towards, tilting it at an angle from the horizontal, from the horizontal towards the center of the circle. So building a road and tilting it at an angle from the horizontal towards the center of the circle. Others also define it as building a road and then raising the end of the road through an angle towards the center. So this is when the road is flat. But when the road is built in such a way that the end is raised, and as a result makes an angle towards the center. That is banking. And as I said, banking is an engineering architecture which provides cars to stay in, or enables cars to stay in a circular path without depending on friction. So banking is an engineering architecture that enables motorists to take a bend without depending on friction. So I think when we come from Xmas break, we'll go into the physics and mathematics of banking. This is the explanation of it. We'll go into what is that component or value which prevents the centripetal force but not the frictional force between the tire and then the road. Okay, so we'll leave that for after. That's not so. This is where I draw the curtains on our meetings today. I'll send you work sets on what we've done, more challenging questions, so you try your hands on. Please, is that okay?
Yes, please.
So until I think 20 something, I'll check and then update you. Okay, please enjoy yourself, take care of yourselves, and then please go to church and then pray so that we can have problem-free Xmas period. Until then, in fact, bye-bye. Take care of yourselves.
Bye.
Bye-bye.
Bye.
Okay.